Hello, class. I just realized I forgot to put my timer on. Boy, that's good, isn't it? Because half the time I don't remember to put it on at all. Um, but I've got a good lecture on Thevenin's theorem today, and we're going to look at a variety of things. But really, let's first just talk about Thevenin's theorem. In my opinion, one of the most important theorems you're ever going to learn. Helps rationalize printed circuit board layouts, circuit layouts, everything. So Thevenin's theorem is an important theorem. I should check and make sure yeah, well, testing. Yeah, I guess I'm on. So anyway, Thevenin's theorem says I can take any circuit. If I want to find a resistor or whatever in any circuit, I can take that circuit and I can replace it with a Thevenin's voltage supply and a resistor in series with that. Now you're probably saying, does that mean that I could also replace it with its equivalent current source and a resistor in parallel with it? Yes, absolutely, because we just learned that source transformation, right? But really, what we're going to be working on today is just to do what Thevenin did, and basically that's saying that we're going to have a voltage source. In fact, really, Norton's theorem is the yeah, Norton got off very easily. Thevenin did all the heavy lifting, I think. Although I haven't gone back and researched that as to who was doing what. And then this would be Thevenin's resistance. So we've got two things, and that then is going to hitch up to the rest of the circuit, right? Whatever your load is, that would go out to some type of load. Well, I shouldn't write impedance, should I? Because you guys are still at the resistance load level. You don't even know what impedance is yet. I'm going to tell you what impedance is. Impedance is resistance plus J reactance, right? That is for your AC, Network Theory 2 class. So remember, impedance, is not resistance. When somebody says they have a 75 ohm coaxial cable, they mean they have a 75 ohm impedance coaxial cable, right? As far as the characteristic impedance of that cable would be. Right. So anyway, so we're still working with resistances here in Network Theory 1. So let's do that. So that's basically, we can take any circuit, and then if we find 2 points A and B, and we're going to do a couple examples of that, we can replace that with a voltage and with a Thevenin's equivalent resistance. I may have to get an extra pen today, a newer pen. Might sort of let that one, I'll put that over there. Is that a new one? Oh, yes. Okay. So I have a brand new Sharpie marker, and what I want to look at, I think the best way to really see this is to just do a couple. I'm going to start with a very simple example, and then I'm going to extend into current sources too, and show how we can turn those into Thevenin equivalent circuits. All right. So the first thing that I want to look at is this circuit. In fact, it's very similar to that circuit that we've got there, a little more complicated. Using the new pen for the first time. I'm going to ground that. And I'm going to say that this is a 9-volt voltage source. And then I've got a resistor here, a 3-ohm resistor. And I also have another 6-ohm resistor. All right. Now that's going out to another load resistor. Remember what I said before about, even this is the load, and we're sort of just cutting it right there, and then we're finding what's over here. And so this is my load resistor, R sub L, right? And what I want to do is I want to find out what is the Thevenins. Can I simplify the equation, the circuit to the left of that line, that AB line, right? So can I simplify this to one current source called the Thevenin's equivalent, or did I say current? I meant voltage. One voltage source, the Thevenin's equivalent voltage, and one resistor. And then how do I do that? What is the process by which we work through Thevenin's theorem? All right. So the first thing that we want to do is we're going to remove voltage sources and current sources. How would I? There we go. Remove all voltage and current sources. So what do? We replace voltage sources with a short circuit. We replace, I'm going to put a line here. We replace current sources with an open circuit. Open circuit, short circuit. All right? So that's what we do first. And I think you can see that we're going to replace that. We really have to cut. I should even put down 0, step 0, cut circuit at A, B line, right? That's what we're doing. We're taking everything. We're basically cutting that circuit now, and we're going to look in that circuit. So what have we got next? So this circuit we've got here now is going to turn into this circuit. There's my 3 ohm resistor. Now, when I go down to look at my, in fact, I'll use a different color pen there to show that I'm short circuiting that, right? And then I still have to draw the rest of the circuit. Right? And this is still A, and this is still B, right? Does everyone see how I've redrawn the circuit and I've put the short circuit in for the power supply? Now, what I'm doing is I want to look in to the circuit in this direction, right? I'm looking into the circuit in this direction, and I want to find the equivalent resistance. So my equivalent resistance is going to equal my Thevenin's resistance, all right? And we know that this is 3 ohms. To make the thing easier, 6 ohms, right? So if I'm looking in here, how would I draw that? What is that from A to B? Now, how could the current flow? Let's say that the current is flowing out of A, right? Now the current could flow, and it could flow through here, couldn't it? The current could also flow all the way over here. So I've got 2 resistors in parallel. I have to figure out what the equivalent resistance of those 2 resistors in parallel are. So my equivalent resistance, which is also my Thevenin's equivalent, my Thevenin's resistance, is just going to be 3 ohms times 6 ohms divided by 3 ohms plus 6 ohms. right? So 18 divided by 9 is 2 ohms. Does everyone see that? So my Thevenin's equivalent resistance is going to be 2 ohms. We could draw our Thevenin's equivalent resistance down here, but really, first of all, that's the first thing we do, right? And then now I forgot to write down the second thing, which is to find the equivalent resistance between A and B. Find the equivalent resistance between A to B, right? That's what we want to do. Find the equivalent resistance between A and to B, and that equals my Thevenin's resistance, right? Does everybody follow me? Okay, now that gives us our resistance. That doesn't give us our voltage source value, right? So the next thing you do is you put the voltage sources plus the current sources back in, right? And I'm going to put a comma there, and find VAB, which is VA minus VB. Find that, and that is going to equal your Thevenin's equivalent voltage source. So that's the next thing that we've got to do. So let's pop that back in there now. And so I'm going to redraw it again. Like this part here is equivalent to 2. And then part 3, right down here, I'm going to stick that back in there. So now I've got a 9-volt power supply, and it's coming out to 3 ohms. And it's got the 6 ohms coming down here. I don't really have to draw it so far anymore. I do want to, keep my ground there and everything. And now I still got A and B, right? And this being a 3 ohm and this being a 6 ohm. All right. Now, look at the current flow when I put the 9-volt back there. Now, I'm still cut this off at, right? We still have cut this off between A and B. Let's not forget that, right? And so we've still got this cut off here from A to B too. This is an open circuit out here. That's how you want to look at it. That's an open circuit. There's nothing connecting A to B. And I say that only because students, for some reason, think that it's still somehow connected. No, it's not connected. I've disconnected it. From here, from that vertex, that node, out to here, it's the same voltage. From this vertex here, out to that node, same voltage. So, and we'll see that when I do another example too. So anyway, let's look at this now and find out what our voltage is. Where can the current flow? Well, the current flows out of here, right? And it's got to flow past that 6 ohm and has to flow back, and it's got to flow in here. So it basically is going to have a voltage drop across the 3 ohm resistor, and it's going to have another voltage drop across the 6 ohm resistor. So what's the current that's flowing through there? What we have to do is we have to find the voltage drop across that 3 ohm resistor, right? So that we can find out what the voltage is at point A. So what is the voltage at A? We know the voltage at B already. The voltage at B is 0, right? Because it's grounded. So the voltage at B is 0, but what's the voltage at A? Well, to figure out what the voltage at A is, we have to find the current that's flowing through this circuit that we've got here. Well, I have 9 ohms and I have 9 volts. So my current is going to be 9 volts divided by 9 ohms, which gives me 1 amp. and my voltage drop across my 3 ohm resistor is going to be the 1 amp times 3 ohms, which gives me 3 volts, which means the voltage at A is 6 volts. 9 minus 3 equals 6. Does everyone see that? So the difference between voltage A and voltage B equals, in fact, I don't really need the dash there anyway, is going to be 6 volts, which also equals my Thevenin's equivalent voltage source. So I can redraw that circuit now, right? I can redraw the circuit now as this. 6 volts I'm still going to ground that, and 2 ohms, right? 2 ohms, 6 volts. And I'm still at A, still B, and now it's going to that last, oops, sorry, did it again. That last resistor, my load resistor for the circuit. Does everybody see how I did that? I don't think, you know, it's all that difficult. You've got to learn how to do, you know, Thevenin's equivalent. But once you do, like I say, it's a very powerful tool. Now, I want to go on and I want to do another example, but an example that doesn't use, and again, Thevenin's theorem always brings it back to a voltage source and a resistor. Voltage source and a resistor in series. Norton's theorem, which we'll get to in the next lecture, is going to bring it back to a current source with a Norton's resistor in parallel. Yeah, I think you know where this is going. Like I say, Thevenin, I feel, did all the heavy lifting. Now, I'm going to draw this circuit. This circuit is a current source circuit. Rather than, and I'm still going to bring it back to a Thevenin's equivalent voltage source and a resistor. But I'm starting, right? It's really the end product that differentiates Thevenin from Norton, not the beginning product. I mean, the final product for Norton's theorem is a current source with a resistor in parallel, right? And Thevenin's is always a voltage source with a resistor in Thevenin's equivalent resistance in series. And they're very closely related. I mean, you can see how you switch between the two different sources. So I think everybody can see that, you know, Norton's theorem was sort of just a natural corollary of Thevenin's theorem. That's what I wanted to say. All right, let's look at this circuit first. This is going to be a 12 amp I don't know if I have enough room up here, but I'm going to try to write it in there. 12 amps. I think I got it in there. And then the first resistor we have here is a 4 ohm resistor. And then I've got another 2 ohm resistor. I might just have enough room here. And then I've got my load resistor out here. So I'm going to put A right there, and I'm going to put B right here. Now, what I want is I want this part of the circuit, right? The Thevenin's equivalent for that part of the circuit. So we're going to be breaking the circuit right there. That's green. I wish that the green came out better. But I'll put red here too, green and red. Of course, to colorblind people, that's just brown. Now, so I've cut the circuit, and what that gives me is it gives me this. I'm going to draw it a little larger. So it gives me the 12 amp current source. Then it comes out in parallel with that 4 ohm, and of course this is grounded, with the 4 ohm resistor, and then I've got another 2 ohm resistor here. Right, so that's what I've got, A, B. So what I want to do, like it says, first thing I do, remove voltage sources and current sources. Replace voltage sources with a short circuit. Replace current sources with an open circuit. So I'm going to replace this with an open circuit. Right? I still want A and B to be on there. So if I replace that with an open circuit, let's just put, I'm just going to put my finger there so I don't have to waste a lot of time redrawing that whole circuit. I'm just putting that there. There's no current that can flow through my finger. Think of my finger as a piece of wood. That's right. So nothing could flow through there, right? There's no current that could flow through there at all. The only place that current, can flow through now is here, right? Does everybody see that? I've removed the current source. So if I've got current flowing from A to B, it can't flow through, my finger, which is just an open circuit. It has to flow through the 2 ohm resistor and then through the 4 ohm resistor and then get down to B. So that immediately tells us what Thevenin's equivalent resistance is, doesn't it? We know that Thevenin's equivalent resistance is just going to be these 2 resistors in series. 6 ohms equals 2 ohms plus 4 ohms. Just for anybody who may not have realized where I got the 6 ohms from. All right, now that was part 2. We finished that. Now what's part 3? Put them back in and find the voltage difference between A and B. Okay, well, we'll do that. We got 12 amps there, right? 12 amps are flowing out of there, and now they've got to flow either down here or out here. Wait a second. Isn't this an open circuit? Isn't that from A to B, just like I was saying over here, from A to B, that's an open circuit. From A to B, that's an open circuit. Is any, with this 12 amps here, let's follow the 12 amps. I'm going to get another color. I'm going to get my orange. So the 12 amps comes out of here, doesn't it? It's coming over here. Does the 12 amps flow to point A? Why would it? Right at this node right here, nothing can flow in this direction. Isn't that just a resistor just hanging on into open air? I mean, there's nothing out here, is there? There's no place for it to go. There's no completion of a circuit. So the only place that this current can go is back down through the resistor that's right here, the 4 ohm resistor, right? And then back into the current source. Boy, even that pen is not that dark anymore. I've got a whole new set. I'll show you. I'm not going to waste it right now. Woo-hoo! Woo! I haven't opened it up yet because I'm still using my old set of colored pens, which actually, now that I look at this, I've got quite a bit of color here. But let's go back to this. So that's right. All that's doing is flowing around in a circle, around through the 4 ohm resistor. V equals IR, right? V, I always write this down, equals IR P equals IV. Let's never forget that. And so what I've got here now is V, Thevenins, right? Sometimes we write it E because EMF, so that's why we use E in terms of V for volts, E for electromotive force. That's what EMF stands for, electromotive force. Anyway, so V equals IR, so I, R, 4, 12, 48. So let's redraw the circuit now. So I've got my Thevenin's equivalent voltage source, which is 48 volts. Sorry, I was thinking of another thing there at the same time. And I'm going to connect that to ground. And then I've got my resistor, which is just the 4 ohms and the 2 ohms. So that's going to be 6 ohms. Right? And that is hitched up again at A and B to my load resistor. Right? So there you go. This is the Thevenin's equivalent. So Thevenin's equivalent, I like the red one. Thevenin's equivalent voltage for this when we started off with a current source, and then Thevenin's equivalent resistance, and that's how we figured it out. So we've done 2 of those. I'd like to do one more. It's a little more difficult. Maybe. I mean, it's just sort of a little more difficult to see. I don't know if I'll be able to finish it on this thing. I may finish it on the next one because Norton's, equivalent circuit is really Thevenin's equivalent circuit just rolled over into Norton's current source plus parallel resistor. So I could spend a little more time in the next lecture working on this problem. This is actually a very nice problem. So I wanted to take a little time to do this too. And I may have the time, but I may not have the room. So let me draw the circuit first, and then we'll discuss the circuit. Okay, so I've got a 6 ohm resistor in parallel, and I'm going to put A and B here. And then I've got an actual load resistor. Let's not worry about what the resistance of that load resistor is, but it's right in the middle of the circuit, isn't it? Then I've got another resistor. It's a little more complicated circuit than we had. Then I also have my voltage source, but I've got it upside down to what we usually do. I've got it pointed toward the bottom now. And in fact, when I say the bottom, we talk about the bottom of the circuit, and most of the time that's been grounded. Oh my God, I've got my positive down here and my negative up here. I wonder what's that going to do to my voltage profile across the circuit. I'll also give you some other information. That is a 4 ohm resistor, 6 ohm resistor, and the power supply is an 8-volt supply. I have one more resistor. So you can see it's a more complicated. This resistor here, by the way, is just a 2 ohm resistor. Yeah, this is really only my second lecture today, but the first lecture, of course, I did twice because I screwed that up. I do have some warm tea, not hot tea. After this, I'm going to heat it up and I think have some lunch and take a break. But But you know, once I get into the lecture, just like when I'm teaching you in person, it more or less just flows. You know, I prepare quite a bit for these, but then once they're going, it flows pretty well. And I think everybody sees how I've got there. You know, I should probably take my large red thing so that you can remember what we did in that first example problem too, right? And then we've got the same ones here. Now, when we look at this, what I want to do is I want to take out this, right? This is A and B now, right? I'm taking this middle one away. It doesn't have to be one that's on the end. It's just any of the resistors. When I give you a resistor to take out and to tell me what the Thevenin's equivalent voltage source and resistance is, I'm certainly not going to put it at the very end like we've done for these last two, am I? No, I'm going to pull it out of the middle here. I'm going to probably put it in the middle of a Wheatstone bridge or something and say, hey, okay, go ahead and do that for me. So, you know, you can't see that too well, but that is, I'm going to 8 volts. All right. So what we want to do now is we want to redraw that circuit. We want to redraw that circuit without the load resistor in there so that we can start making sense out of this, you know, going from A to B. You know, to solve this though, let's do the first thing. So the first thing we do is remove all voltage and current sources, and we redraw the circuit. And we redraw the circuit from A to B, don't we? Let's do that. Let's say that this is A. I'll start from this, no, I'll start from this end because otherwise, but I hope you guys can see it. So let's redraw the circuit from A now, putting a short circuit right where this voltage supply, this voltage source is going to be. So A comes out to a node, doesn't it? Right? Comes out to a node. And at that node, we can either go straight through a 6 ohm resistor to B, or we can go out all of this other way, right? So, whoop, straight to B. And you know, where is B? B is down here, right? So we can go straight down to B through a 6 ohm resistor. I hope I haven't lost anybody, right? All I'm doing is putting this branch of the network in from A down to B. Now we do know something about B, don't we? We know what the voltage at B is. B is right down here. And so it's grounded. So we know that the voltage at B is going to be 0 volts. Right? Do we know what the voltage at A is? Well, no, not yet. We're still trying to redraw the circuit. Now, the other pathway that's going to go here, right? We have 2 pathways at A. We have one going through the 6 ohm down to B, just like we've drawn. We also have one going through a 4 ohm, right? So that's going to be a 4 ohm resistor. And then when we come up to this, we've got another node right here at the end of that 4 ohms, and it can either go through a short circuit down to B, right? It can go through a short circuit down to B, or it can go through 2 ohms down to B. All right? Now, let's look at the current flow that's occurring when we're figuring out our Thevenin's equivalent resistance. Let's look at the current flow. Now, the current will flow through here. Some of it would flow right through here. Some of it would flow through here. When it gets to here, this is going to flow directly to ground, right? Does any of the current ever get to the 2 ohm? Let's do an analysis. So this This right here is 0 ohms, and that's 2 ohms. Well, let's see. So my equivalent resistance for the 2 ohms and the 0 ohms is going to be 0 times 2 divided by 2. I'll do that one, 0, right? So it's 0. So the only current that's flowing around there is flowing through that 4 ohm, then it's going down and reconnecting with what's coming through the 6 ohm straight to B. This might as well, the 2 ohm might as well not even be here, right? The 2 ohm in our analysis might not even be there because we've already short-circuited this, right? This has been short-circuited, which means that the current would flow right through there, obviating any current flowing through the 2 ohm, right? All right. So what we've got here now is current flowing through a 6 ohm and current flowing through a 4 ohm. So let's figure out what our equivalent resistance is going to be, which is also our Thevenin's equivalent. And wouldn't that be 6 times 4, 6 ohms times 4 ohms divided by 6 ohms plus 4 ohms, right? So my Thevenin's equivalent resistance is going to be 24 divided by 10, or 2.4 ohms, right? And since I'm circling all of the other ones in red, I will circle that one in red too. We have gone a little long, and I think that I think I'll finish up the Thevenin's equivalent current in the next lecture that we do. All right, so come back and we'll finish up the Thevenin's equivalent circuit. I don't want this to go too long. We're already past my alarm, and like I say, Norton's is passe because it really is just an extension, in my opinion, out of Thevenin's, even though I'm sure that they were independently, come to the same conclusion. All right, on to Norton's theorem and finishing up Thevenin's equivalent theorem for this example problem that we're doing. See you there.